hopefully we can make them online.
Mm-hmm.
Okay, so we're gonna have Will Perkins today to kick off the talks with talking about zero-free regions and repulsive gases.
Okay, thank you. Thank you all for coming to this reunion. It's been really fun so far to see you all again and talk about some of the themes that have developed since the program. I'm going to be talking about a classical problem in statistical physics, classical gases. And so this is really the original statistical physics model. And what I want to present is a new result that really came from ideas that came out of this program that I attended. So this is joint work with a postdoc at UIC, Marcus Michelin. He also actually attended I think the workshop on beyond randomized rounding. He spoke there. So there's some good connections. Okay, so what will I talk about? I want to talk about this classical model and then give some of the history and present one really major open problem that is a bit out of reach, but at least I would like to mention it. Then I'll talk about some of the classical results from the 1960s on in this field, and also try to develop analogies with discrete models, so spin systems that people might be more familiar with. Then I'll present this new result that came from some of the ideas of the program. And then at the end, I'll talk about some more manageable open problems that are still quite interesting, but not as hard or maybe as exciting as this major open problem. Okay, so for me, some of the themes of the program were, one was the relationship between these different approaches to approximate counting. So Markov chains, the correlation decay method, and Barbanak's polynomial interpolation method. We actually saw some, just this week on Tuesday and Wednesday, saw some nice talks really about this theme. And so before this talk started, Guus and I were talking that really since the beginning of the program, this area has seen a lot of development. We really do know a lot more about the relationship between these notions of approximate counting, which is quite cool to see. And then the other sort of more vague and broad theme for me was just the influence that different fields have on each other. So in particular, you know, a lot of the problems that we study in algorithms, for example, maybe come from statistical physics, and you know, combinatorics and algebraic geometry is involved in this program. What I want to talk about today is how some ideas from algorithms really, you can go back and answer some questions in this original questions that they're asking in statistical physics. So that will be the direction today. Okay, so here's my very vague and broad view of like, what is statistical mechanics? What's the goal? And I think the goal is to be able to derive the macroscopic properties of fluids. And so here I include all the different states, so gases, liquids, and solids, just from microscopic interactions. Can the interactions between molecules and then put out to a large system, can this actually explain these big phenomena that we see and the different states of matter? That would be very appealing if it's true. And of course, this dates back a long time. So Maxwell, Boltzmann, and Gibbs in the 1800s sort of started this, precise way of looking at statistical mechanics. Oops. Oops. Okay, and then many of the most important mathematical results in this classical setting were proved in the 1960s. So Penrose, Ruel, Leibowitz, Grunewald, Lieb, and even earlier, so Meyer and Li and Yang. I'll just underline two. So for me, one of the highlights of the program was the workshop where Ruel and Lieb gave talks. So that was quite impressive that they're still going, but they were really proving some of these foundational results in the 1960s that I'll mention. Okay, and so what's the rough idea of this classical model? It's that we represent a gas or a liquid as a collection of particles moving in the continuum. And the particles will interact with each other in some way. So there's some interactions between particles. And as we change, say, the density or the temperature, we hope to see that, in one state we have disorder that represents a gas, and then as the density increases or the temperature decreases, maybe some long-range order emerges. So on the right, we see some sort of crystalline lattice-like structure emerging from this random collection of molecules. So that's the vague picture. The precise model is the following. So we define an energy function that takes finite point sets in Euclidean space. So if you're a physicist, you should take D to be 3 or D to be 2 for the rest of the talk, but computer scientists, you can take D to be anything, 10,000. But this energy function will spit back a value that's a real number, positive or negative, or plus infinity. The points will live in some bounded region lambda in Euclidean space. So you think of this as a box, if you like. And two parameters we have are the activity parameter, which somehow affects the density, and beta, the inverse temperature, which will affect the interaction strength, how strong the interactions are. And then the model is quite simple. So if you know a Poisson point process, so you have a region in Euclidean space, a Poisson point process is basically the prototypical non-interacting process. In any region, the number of points you see is a Poisson distribution, and in two disjoint regions, the number of points are independent. So we take a Poisson point process, but then we put a density against it, and the density adds the interaction. And so the density against the Poisson point process is e to the minus beta times the energy. And this adds the interaction. Okay. And so this is the model. So now we have an interacting, a random point set or a point process in our bounded region, capital lambda. Okay, and then that's quite a general model because I've allowed this energy function h basically to be anything you want. But I'm going to specialize to the most studied class of energy functions, and that would be a pair potential. And so now the energy function will just be the sum over all pairs of particles, some pairwise interaction. And this pairwise interaction maybe just depends on the difference in the vector difference between these points. And it can take real values or plus infinity. Okay, so if you have any questions about the model, please shout, or I have the chat open, so ask in the chat any question you have. For the purposes of the results that I'll present, a special case of a pair potential is a repulsive potential. And that's where the pair potential is non-negative. Okay, and so what this means is that points only repulse each other. There's no attractive component. Because remember, this appears in the density as exponential of minus. So phi greater than or equal to 0 is repulsive. Okay, very good. So a special case of this model, and maybe one you've heard of before, is the hard sphere model. And this is my favorite model to look at and our initial motivation when looking at this stuff. So the potential is just the following. The potential takes the value plus infinity if the distance between points is less than some number r, and 0 otherwise. So the only interaction is this hardcore repulsion. 2 points of the point process are forbidden from being within distance r. And so the point process actually represents the centers of a sphere packing of balls of radius r over 2. So here we see some realization of the hard sphere model. And this is actually literally exactly the hardcore model. This model we've seen several times in the workshop already. This is a hardcore model on an uncountably infinite graph. Right? So the vertices of this graph are the points of this region lambda, and 2 points have an edge between them if their distance is less than r. So it's literally a hardcore model on an uncountably infinite graph. Okay, and this particular model also is, maybe this is the original statistical mechanics model. In terms of mathematical results about it, these were proved back in the 1890s. Van der Waals and Boltzmann, they were interested in something called the virial coefficients. Virial coefficients, these are actually somewhat related to the topic of the program. These are the coefficients of an infinite power series for a logarithm of a partition function. So they were already interested back then in computing these things. There's also a nice long association with computer science. So you may know that this Metropolis algorithm, the Markov chain Monte Carlo method, was invented to sample from the two-dimensional case of this hard sphere model. I have a picture of the original paper on the next page. And importantly, the physicists do believe that this exhibits a phase transition. So from a gaseous disordered state to a crystal state in dimension 3. But even on the level of physics, things are still not completely understood. So dimension 2 is much more subtle than dimension 3, and even the best predictions even are only about 9 years old, and I'll show you on the next slide a little bit. But these predictions actually were driven by a new algorithm. So event chain Monte Carlo allowed them to do simulations of a much, much bigger size. So there's this nice close connection between understanding this physical model and algorithms. Let's see. Okay, so here's just a couple of pictures of old papers for you. So on the left is this original Metropolis algorithm paper. So a general method suitable for fast computing machines is described. Results for the two-dimensional rigid sphere system have been obtained on the Los Alamos Maniac and are presented here. So this is the start of the Markov chain mania. On the right is this much more recent paper. This is the 2011 paper where they describe this hexatic phase transition in 2 dimensions on the level of physics. But you see, like, to determine these properties, they were doing enormous simulations at very high densities using a Markov chain. And maybe for those of us who are theoretically inclined, I think that the really interesting thing about this algorithm they have for sampling is that it's non-reversible. And somehow the non-reversibility lets them study much larger systems. So non-reversibility helps sampling, which is kind of interesting. But those are some nice pictures in their paper. Okay, so back to the general setting. What are some basic questions about this classical model of a gas? And so, the first question, of course, is this a reasonably accurate model of a fluid, a gas, liquid, solid? And does it actually exhibit the same phase transitions that real fluids do? That's probably the most basic question. And of course, we should choose the right pair potential. What pair potentials are physically realistic? So the hard sphere potential, as far as I understand, this is fairly realistic, or thought to be fairly realistic, in terms of the gas solid phase transition, but maybe not realistic as about liquids. Something called the Leonard-Jones potential. This is perhaps thought to be much more realistic. I'll sketch it. It's strongly repulsive at short range, and then it becomes weakly attractive and decaying, but it's an infinite range potential. So that's supposed to be an asymptote. This is the Leonard-Jones potential. And so you see there's a strong repulsion, large positive numbers at short distances, and then an attractive component, a weaker attractive component at long distances. And so this is the type of pair potential that people think is actually a realistic model of one of these substances. Okay, and then what mathematical properties of a model like this correspond to the different states of matter? And there's some decent answers here, and these relate to, say, correlation decay. So maybe in a gas, we should expect exponential decay of correlations, whereas in a solid, we should expect long-range correlations. You can also define this in terms of mixing times, maybe of Markov chains. And as mathematicians, of course, we can ask, can any of these properties or results actually be proved? And that would be the ultimate goal, to prove that this model that just is determined by these microscopic interactions, prove that it exhibits all these properties that we expect in real fluids. Okay, so now I want to talk a little bit about what has been proved. And as you know, mathematically, at least in this model, phase transitions only happen in an infinite volume limit. And so what are the basic objects? And so here, now we get into polynomials. So we have the partition function. And what's the partition function? Again, we have this activity and we have our region lambda, capital lambda. And so we sum over all numbers of particles, lambda to the k. So the activity is an exponential weight divided by k factorial, and then integrate over all k tuples of points, exponential of minus the energy. Okay? And from now on, I'll probably ignore the beta and just put the beta into the potential. So that's the partition function in finite volume. Notice that if the potential has a hard core, so if there is some plus infinity interval around 0, then there is some max packing. And so this sum actually is a finite sum. It becomes, the terms become 0 after a certain n. And then we really have a polynomial in lambda here. But the coefficients now they're not integers, they're integrals, multidimensional integrals. Okay, and so to see what happens in the infinite volume limit, we can take a limit of the log partition function, take the log, divide by volume, and let the size of the box tend to infinity. And this defines the infinite volume pressure or free energy. And under some mild conditions on the potential, this limit exists. And then we can ask for its properties. And one nice way to describe or to define a phase transition is its non-analytic point of this function, the pressure in lambda on the positive real axis. Okay. So you can also, of course, define phase transitions in terms of uniqueness and non-uniqueness of the infinite volume Gibbs measure. But let's stick with this non-analytic point to be the definition of a phase transition. Okay, so what's believed? It's believed that actually for a very wide class of pair potentials, they do exhibit phase transitions. And there's a nice survey written about this you can look up if you're interested. It's called the crystallization conjecture. And it's even quite interesting at 0 temperature. But the crystallization conjecture basically says that as the activity goes up or as the temperature goes down, you should expect some symmetry breaking. So you should expect to see actually some lattice structure in the typical configurations, at least in dimension 3. So that's the crystallization conjecture. And here's the bad news. So for the model I've described, a monatomic classical gas, monatomic meaning that there's only one type of particle, interacting via a pair potential, there's not a single example where we know of a phase, that we can prove there's a phase transition. So that is unfortunate. I'll mention that there's some other types of continuum models, multi-type or multi-body models that have been proved to have a phase transition, the Whittam-Rowlandson model. But this is a very different type of phase transition. It's like two types of particles that exclude each other, and it's sort of like an invasion type phase transition where one particle dominates. So it really doesn't correspond to this gas-solid phase transition that the model is supposed to, this classical model is supposed to capture. And so that's the major problem that I wanted to bring to your attention. We have this great mathematical setup for this model. It's been observed in simulations that this really does capture the property of real fluids. But mathematically, we can't prove that there's a phase transition in any such model. And so it would be great to revisit this. I mean, surely it takes some really, really big new ideas. But I think this is a great problem to have in the back of your mind. Let me just, I'll give a hint. I mean, this may or may not be useful, but try dimension 24. So, you know, it'd be nice to prove this in any dimension, but dimension 24 at least has the positive thing that we know a lot more about the best sphere packing in dimension 24. There's this Leach lattice. It's a really, really good sphere packing, and we can prove a lot of interesting things without so much effort. It's much easier than, for example, dimension 3.
What about 8? 8 should be easier.
Or 8, yeah. Good, thank you. Yeah, 8 and 24. Those should be the first places to try. Exactly. There's another really good sphere packing dimension 8. Okay, so this is a bit of a bummer, I would say, that we can't prove this, but there's silver lining. And so one of the consequences of the failure to prove this is that lattice models became popular. Okay, so where we discretize and put spins on lattices, so Ising model, hardcore model, monomer dimer model. And for many of these models, this argument of piles for the Ising model can actually be used to prove the existence of a phase transition. And so the silver lining is that like somehow discretizing actually maybe encouraged this collaboration with combinatorics and computer science and led to.
I'm sorry, but Pierre's argument, it's a completely different phase transition, right? It's not what you were looking for.
Oh, it depends on what you mean completely different. So you can do a piles argument to show that the hardcore model on Z2 has a phase transition.
A phase transition meaning that correlation.
Yeah.
But you want analyticity.
Well, it also means that there must be a non-analyticity in the pressure.
Is that right? I mean, in general.
Yeah, because I mean, you can't I mean, I'll show you actually. This is like a very classical result, but if you have analyticity all the way from 0 to infinity, then you have to have uniqueness as well. If you have uniqueness in a ball.
Okay.
So that it's not like a one-line argument, but you can use like some classical complex analysis theorems. But if you have analyticity in a region containing 0, and you know that you have uniqueness in some tiny neighborhood around 0, then you have uniqueness all the way up.
Ah, okay. Yeah, thank you.
So yeah, so there must be a non-analytic point in, say, the free energy of the hardcore model on Z2. But you're right that it's quite different. It's somehow a bit cheating because by putting it on this bipartite lattice, we insisted that there's only 2 ground states. And so this makes arguing about the ground states much, much easier. But yes, so that this is why perhaps these discrete models have taken off, while the continuum is sort of not studied as much now. In fact, most of the results, or almost all the results about the continuum model, just pertain to the gaseous state. So the results are about absence of phase transition at low activity or high temperature and consequences of this. Okay, so here's a really nice paper to read. Yang and Li, or Li and Yang, in 52 wrote 2 papers, part 1 and part 2, about phase transitions. Part 2 is maybe like one of the touchstone papers of this program. It's about the Ising model and the fact that the zeros lie on this disk. Part 1, though, sort of sets the stage, and part 1 proves that and the setting is classical continuum gases, they prove that a 0 free region in the complex plane implies the absence of phase transition in terms of the non-analyticities of the pressure. And so this is a great paper to read. It's 4 pages and full proofs are there. They do require a hardcore so that they're working with polynomials. But otherwise, it's exactly the model I've set up. And this really provides a connection between complex 0 free regions and absence of phase transition. Okay, and then, so what results are known? So realistic potentials, as I said, should be strongly repulsive at short range and weakly attractive at long range. 2 definitions. One is a potential is stable if you take any collection of points and sum over pairs, sum the potential over pairs. This should be, if it's stable, should be at least minus b times the number of points in this set for some constant b. And so, okay, so for repulsive potentials, of course, it's non-negative anyway, so you can take b to be 0. But if you have an attractive part, your potential may or may not be stable. If you're not stable, if you don't satisfy this, then very often you can have catastrophic behavior. And so infinitely many points can condense in tiny regions. And so you actually can't even take a thermodynamic limit. So stable is a very natural property. Tempered is just a way to say that the long-range interaction is not too strong. So the interaction strength decays. So this integral of 1 minus e to the minus potential is finite. And this constant, the temperedness constant C phi, this will play a large role in all the classical and new results on the model. Okay, so those are two definitions. Let me say that if you want to read anything about these classical models, almost all the results and proofs are contained in this great textbook, Statistical Mechanics, Rigorous Results. And many of these results are still the best known results. The one exception might be that statisticians have studied these Gibbs point processes from the perspective of sampling algorithms. But otherwise, for these classical results about these processes and absence of phase transition, this book is essentially up to date, and it's very nice to read. Okay, so the most general result about absence of phase transition is from 1963 due to Penrose and Ruel independently. And their result is that for any stable tempered potential, this infinite volume pressure is analytic when lambda, so complex lambda, is at most 1 over e to the 2b plus 1 times this temperedness constant c. Okay, so it's 1 over c, and then in the denominator e to the 2b plus 1, where b is this stability constant. Good. And for repulsive potentials, right, we can take b to be 0. This is just absolute value of lambda is at most 1 over e times c. And this was proved earlier by Grunewald. Okay, so that's the classical result. And this level of generality to date, the Penrose-Ruel result is the best known. So there's been no fully general improvement to this bound since then. The proofs of these theorems, or this theorem, is by convergence of the cluster expansion. What's a cluster expansion? Well, this really is the Taylor series for the log partition function around lambda equals 0. So exactly what we look at if we do the polynomial interpolation method. And we want to know, does this converge? Absolutely, as a power series. And this Penrose-Ruel result says yes, if lambda is at most that bound. What's interesting is, and I didn't know this before, they prove convergence via something called the Kirkwood-Salzburg equations, and showing that in this region there's a unique fixed point. And so I think it would be interesting to look perhaps for algorithmic applications of this method for proving convergence. On the other hand, for repulsive potentials, Grunewald also showed a negative result. The cluster expansion cannot converge if lambda is at least 1 over c. So it does converge for lambda at most 1 over e times c, but it can't converge for 1 over lambda bigger than 1 over c. And if you have read this Scott Sokol paper, you'll know that for repulsive potentials, the closest singularity, so the closest complex 0 of this partition function, is actually on the negative real axis. Okay, and so this is not physical. This is preventing convergence of the cluster expansion, but it doesn't actually have any relevance to the physical question of phase transition. And so one question is how to avoid this. How can we analyze this gas without running into this problem of the negative singularity? Okay, so there's some different approaches. If you just care about positive activities, of course, you can use probability. Right? Things are probabilistic with positive parameters. And so for the special case of hard spheres, there's been some progress in this regard. There's an idea of disagreement percolation that actually comes from the discrete setting. And in the case of hard spheres, so for hard spheres, the cluster expansion bound gives you 1 over e times c. The disagreement percolation bound for hard spheres will give you something like 1 over c, at least in large dimensions. Another approach is Markov chain mixing, and you can look at fast mixing for some Markov chains. And this has been studied in quite a few papers. There's the Gros-Jerram papers about perfect sampling. So last year with Tyler Helmuth and Samantha Petty, we looked at this for hard spheres. One thing we did was we sort of we extended this notion of equivalence of spatial and temporal mixing to the continuous setting, and so showed that if you have like n log n mixing of a certain Markov chain, you get strong spatial mixing. And we also use this idea of path coupling with an optimized metric due to Vagoda in the case of hardcore. And I'll have a chart comparing this to hardcore in a second, but then we improved for hard spheres the bound to 2 over C. Okay, so this is beating the classical bound for analyticity by a factor 2e. But again, this is only for hard spheres. And this really, all these methods really, at the moment, just work for hard spheres.
Will, can I ask a quick question?
Yes.
So this C, should I think of that as the maximum degree in the discrete setting, or is that completely off?
Yeah, that's actually a great analogy. So for hard spheres, this C is literally the excluded volume. So the volume of points that, if you put a center somewhere, the volume that you exclude, and this is exactly like in hardcore, it's your degree. So yes, there's the next slide will have a nice table of analogies, but you got that analogy exactly. Okay, so here's the analogies. So a monatomic gas, we say there's just one type of particle, so either there can be a center present or not. And so this corresponds analogously to like a 2-spin model, presence or absence of a particle in the discrete setting. We've said that somehow the hard sphere model is like the hardcore model. Now we have, for the hardcore model, we have the shearer disk. Like Hus said, we should think of the maximum degree. When do we have convergence of the cluster expansion in terms of maximum degree? It's as delta gets large, this is like 1 over E delta. And correspondingly, for a repulsive gas, we have convergence of cluster expansion for absolute value of lambda less than 1 over E times C. So exactly this analogy between delta and C. Anti-ferromagnetic in the discrete case sort of is repulsive in the continuous case. Ferromagnetic, on the other hand, it doesn't really have an analogy in the continuous case, because if you have a purely attractive potential, you'll have this catastrophe of infinitely many points condensing. Another analogy is maybe a more precise analogy. If we think of the d-dimensional hard sphere model, we should think of like the hardcore model on a 2 to the d regular graph. And in fact, even more, we should think of it as locally tree-like. Because actually in high dimensional Euclidean space, somehow Euclidean space is almost tree-like. You can take that to mean what you want. Let's say some other analogies. Path coupling, the basic path coupling argument for hardcore gives you something like 1 over delta, fast mixing below 1 over delta. You can do that very easily for hard spheres and get 1 over C. If you do this optimized metric technique, this Dyer-Greenhill bound or the Vagoda bound, you get 2 over delta, and same with hard spheres. Of course, the 2 over delta is not the last word. You know, somehow the optimal bound is the White's bound, E over delta. And the question, that's the real question that we had, is can you do this White's argument in a continuous setting? And the answer is yes. So the main result is, if you take a classical gas with a repulsive tempered pair potential, then we have uniqueness and analyticity of the pressure for lambda less than E over C. Okay, so, so this beats this known limit of cluster expansion convergence by a factor of E. I think this is the first improvement since the 60s in the general setting of repulsive potentials. And also, even for the special case of hard spheres, we get some improvement, E over 2. But that's the main result. And you know, you should think of this E over C as very analogous to the White's bound E over delta. And that's what we're going to try to do. So any questions here? Okay, so what would we try to do? We wanted to try to somehow adapt the White's argument to the continuous setting. When we were working with hard spheres, we wanted to show strong spatial mixing. Then we were told that actually, like, finite range is a quite severe restriction on potentials, and people are more interested in potentials with infinite range. And there, strong spatial mixing becomes rather hard because you have some correlations at arbitrary distance just from the potential. And so then we realized we wanted really to prove a zero freeness result and use the Yang-Lee program. And here, there's this nice connection that we've heard this week already, but the connection between correlation decay on the infinite tree and zeros of the partition function. So the Peters-Rex paper for hardcore, the two different papers of Liu, Sinclair, and Shrivastava, and a nice paper about potential functions and complex contractions by Xiao and Sun. These were all very helpful to us in trying to understand this. So what are the difficulties? The main difficulty is that the basic building block of this correlation decay method is this recursion for spin ratios of spin probabilities. And what is that? Could that possibly be for continuous models? Even more maybe mysterious is what is an infinite tree in the continuum? And maybe a little more mild, but often these zero free arguments go by induction on the number of vertices of graph. How do you possibly do this if your graph, quote unquote, is uncountable? So these are the difficulties. A couple tools we'll use. One is that it actually helps us a lot to work in the multivariate setting. So instead of activity parameter being a constant, now we think of the activity as being a function on Euclidean space. Okay, either to non-negative reals or to complex numbers. And now the partition function, instead of having lambda to the k, well, it's just a product of the lambda functions over the k points. And then we need something to work with, and we can't have occupation probabilities, of course, but we have densities instead. And the density, one way to define it is it's the function on Euclidean space that when you integrate it over a region, it gives you the expected number of points that fall into that region. On the next slide, I'll tell you a different definition. And one of our goals was to completely avoid the use of probability. We just want to work with these partition functions and densities in some setting. But if we want to work in the complex parameters, we really shouldn't be using probability at all. Okay, so we need a connection between the partition function and densities and a recursion for the densities, most importantly. So here's one way to define the densities that can be generalized to complex activities. It's that the density at x is, well, it's the activity at x, and then times the ratio of two partition functions. In the denominator, we just have the partition function. And in the numerator, what we're doing is we're taking that activity function lambda, but we're squashing down the activity at points that are interacting with x. Okay, so you imagine if your potential is a hard sphere potential, then what you're doing is you're zeroing out the activity in the ball of radius r around x. Okay, so now we just have the ratio of two partition functions with different activity functions, and the first is just a squashed version of the numerator is a squashed version of the denominator. And this definition, of course, works. It's just a ratio of a ratio. It works as long as the denominator is not zero. So we better be careful of that. And our definition here, what do we want to say? We want to say an activity function is totally zero free if you contract pointwise at all. So for every lambda prime that you can obtain by pointwise contraction. So here alpha is a measurable function on Euclidean space to 0, 1. And so if you multiply lambda by alpha, you get something where all the absolute values are just shrunk, but point in the same complex direction. We want this to be non-zero for all lambda prime. So that's totally zero free. It's some sort of hereditary zero freeness. And what we'll eventually prove is that if lambda of x lies in some small neighborhood of this interval of the real line we're interested in, then we're totally zero free. Okay, so two identities, and I wouldn't try to parse these completely, but just to give you some flavor, what type of objects are we working with since we can't do these discrete recursions? The first identity is an identity for the log partition function, and the lemma says, if lambda is a totally zero-free activity function, then you can write the log of the partition function as an integral of some densities. And these densities are with respect to some, again, squashed activity function. And here we're squashing in some sort of ordered way. So capital lambda of x is just a way to say, these are the y's that appear before x in some ordering of points. And what you can vaguely think about is this is somehow like a telescoping product. So that's one identity. But the main ingredient in this White's argument is the recursion. And so here he works with the ratios, occupation over non-occupation probability. And on a tree, to start with in his paper, he writes this nice recursion for the ratios where RV is lambda over 1 plus, and then the product over some ratios where TI is the subtree rooted at VI, the ith neighbor. Now, if you like really squint and make things blurry, you imagine in the continuous setting, well, the occupation probabilities are 0, but so they're really tiny. 0 is very small. So you can imagine that the ratio really is just the same as looking at the density. So you can forget about the dividing by 1 minus. And then you have like lambda over 1 plus, and then a product of lots of very, very small things. You can almost imagine that this is like lambda times exponential of minus something. And this minus something, well, it's, if you take a log, this is like a sum, so maybe it's like exponential of minus an integral of something. Okay, so that's very vaguely thing. If Piyush is asking, should the recurrence be lambda over product 1 plus, I'm sure you are correct. You know much more about it than me, so sure. Thank you. I guess that makes even more sense if we're talking about the exponential, so thank you. But here's the theorem. So suppose lambda is totally 0 free, and then here's the recursion. The density at x is, well, the activity at x times the exponential of the integral of some, okay, we're gonna hit this with the interaction, but also look at some strange densities that again are densities with respect to some squashed activity function. And this is really like what we work with all the time. It's the recursion that we'll use. But the point is that it's an integral identity now. And good. So, and just as you would do in the discrete case, once you have this recursion, you can use it to define a functional. And now we're thinking of this functional as taking a complex number lambda as an input and a density function rho. So a function on Euclidean space. And the functional is just exactly what the recursion defines. Okay, and then once you have this set up, then you can sort of do what you would want to do in the discrete case. We want to prove that this is contractive, after applying a pseudo potential function in, and it is contractive exactly for lambda less than E over C. And actually proving it's contractive is easier than in the discrete case. Somehow this has a nice form. I mean, you can imagine if rho is constant, then this is just lambda times e to the minus rho times c of phi. Okay. And that's where you start improving the contractiveness, is looking at constant functions. And so that's where the c comes in. Okay, and then contraction tells us that if your densities and activity lie in some certain complex neighborhood, then applying this functional keeps you in this neighborhood. And just as Peters and Rex do in their paper. And then, of course, there's no induction. You can't do induction, really. But what we do is sort of an analytic induction. We start with the identically 0 activity function, which, of course, is totally 0 free. And we actually show that if you're in this contractive regime, then if you're totally 0 free, you can extend the region a little bit. Like you can't actually be on the boundary. And this allows us to sort of lift the activity function from the identically 0 function, increase it, increase it, increase it, and prove that it's totally 0 free if it pointwise lies in this neighborhood. So that's the induction, sort of by unsquashing the activity function. Okay, so that's all I wanted to say. I'll leave you with some open problems. I think the biggest open problem and the most interesting one for mathematical physicists would be that this class of stable tempered potentials really is the most natural class. And this is the, the Penrose-Ruel bound that hasn't been improved. This includes like the Leonard-Jones potential. And really, most of this, the identities go through. The question is like how to prove it, the contraction, and what to aim for. So one difficulty, as opposed to the discrete case, is like I don't know actually an a priori bound on the density, because you can put a lot of points with an attractive part around you, and so there's no like obvious upper bound on the pointwise density. Another direction to go would be, can you use this to do some deterministic algorithms? So for hard spheres, at least, we can say that since we get strong spatial mixing, then a certain Markov chain mixes fast, but it would be nice to come up with the right notion of deterministic algorithm in this setting. Another I mentioned was, are there algorithmic applications of this Kirkwood-Salzburg approach to showing convergence of cluster expansion or zero freeness? It's quite an elegant argument, in fact, and you can see this in Ruel's book. Another would be like somehow this argument should be tight. We can construct an infinite tree-like object, but is there a more natural space where you could say, I want to do this particle, this statistical mechanics model in this random space where this argument is tight and where there is a phase transition. So is there a random graph analog for continuous particle models? And that's it. Thank you.
Questions?
So do you also get fast mixing for Markov? Oh, you get because of this, because it's in a lattice or in a like.
Yeah, exactly. Euclidean space is like, I guess, amenable. It has polynomial growth, and so you can imagine the type of results, equivalents of spatial and temporal mixing that go through for lattices go through here.
So is there any, I mean, is there any conceptual obstacle to discretizing this kind of problem? So you have a polynomial of finite degree. So you could imagine trying to get a sequence of polynomials converging to it that are partition functions of some finite models. But
yeah, so there is a conceptual barrier, and that is that we actually don't know discrete models as well as we think. Because there's the only time we know that there's a phase transition in a discrete model of this type is when the number of ground states is bounded. Like it's bipartite hardcore or tripartite hardcore. If I define sort of a lattice where the number of ground states grows with the number of vertices, sub-exponentially, but then we have no idea how to prove a phase transition. And so, yeah, so you can phrase the main difficulty, I think, in a discrete model. It's this bipartite is like so strong that it makes things a lot easier.
Thanks. Yeah, really nice talk.
No, thanks.